Let's look at intermolecular forces, and let's look at the first question. Determine the IM forces in the following compounds. So the intermolecular forces in the following compounds. So here is oxygen, bromine, sulfur trioxide, and hydrazine, N2H4. So looking at the first two compounds, oxygen and bromine, both of them are diatomic molecules. Oxygen is fairly small. So I would say there's hardly any intermolecular forces in this one. For bromine, I should say that there's dispersion forces in there because now the size is larger. So the size, the atomic size, okay, the atomic size is large. So because of that, you should see some dispersion forces, okay, in this. Sulfur trioxide is a compound, of course, so let's go ahead and draw the Lewis structure for this. And we can see it's very symmetrical. And so if it's symmetrical, then it doesn't have a dipole moment. However, it will have a little bit of dipole moment in presence of another molecule. So for example, if another sulfur trioxide were to approach this, then you would have some sort of intermolecular force, and that is because there are polar bonds in there. So oxygen is more electronegative and sulfur would then be less electronegative. So because of that, there is slightly a dipole-dipole force. So not because of dipole moment, but because of the polarity of the bonds. Okay, so dipole-dipole forces. And then for N2H4, well, since there is nitrogen and hydrogen, my first thinking is, okay, I got hydrogen bonding going there. So, but if I draw the structure out, then it becomes even more evident, okay, that I should have H bonding. So that is how you would decide which compound has what kind of intermolecular force, all right? Look at the size, look at the structure, and then, of course, look for hydrogen bonding, where if you have nitrogen, oxygen, or fluorine bonded to hydrogen. Okay, next question. Which of the following pairs has the higher boiling point? Higher boiling point means we are looking for higher intermolecular forces, okay, in this one. So here we have phosphorus pentabromide and carbon tetrafluoride. So let's draw the structure of both. So PBr5, Br, and that's the Lewis structure. Almost, I'm not drawing the lone pair of electrons. There's none left on phosphorus. And then carbon tetrafluoride is this tetrahedral structure. This is trigonal bipyramidal, the phosphorus pentabromide. Both of them are symmetrical. Okay, and so if they're both symmetrical, then there is no dipole moment. If there is no dipole moment, I can't really talk about dipole-dipole forces. However, I can look at the structure of this one and I can say, well, this has got a higher molecular weight, okay, because of the bromines in there. So because of higher molecular weight, this one should have higher dispersion forces. So because of higher dispersion forces, PBr5 should have a higher boiling point. Let's look at the next one where we have SF6 and Ci4, so sulfur hexafluoride or carbon tetraiodide. So again, carbon tetraiodide, again, it's going to be tetrahedral. Sulfur should be like this, octahedral structure for this. And again, look at this, how different this is. We've got 4 iodine attached to carbon. So because this one has a higher molecular weight, this one should have higher dispersion forces. And if you have higher dispersion forces in this one, then Ci4 is going to have the higher boiling point. Okay, that's how my thought process is working for this. Okay, let's look at C. And C is where you have CH3, CH2, 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 CH3, all carbons and hydrogens. And in the next one, I have CH3, CH2O, CH2, CH3. So now I have at least one atom, that is oxygen, which is higher electronegative. But in this case, in the first one where I have CH3, CH2, by the way, this is pentane, there is no electronegative element, there is no polarity whatsoever, so there is more dispersion forces here. Whereas in this case, I can draw the structure out, and oxygen is in the middle over here, so this would be OCH2, CH3, and this would be CH2, CH3, and oxygen has two lone pair of electrons left. So here now I have a dipole moment, and because of the dipole moment and also because of polarity of the oxygen, now I have dipole forces. So because of dipole forces, this is higher boiling point. So that is how you can decide. Just compare the different forces in there. There was no hydrogen bonding in here for question number 2, but otherwise that's how you would decide which one is higher boiling point.